Hello, AI enthusiasts. Welcome to a new deep dive. Building on our previous talk about naive Bayes, let us explore K-means clustering. Most videos on unsupervised learning never show the physical intuition behind the math. In this video, we want to show something different: the invisible magnetic fields that organize your data into clean, logical groups. Think of your data as thousands of tiny iron filings scattered on a table, waiting for a force to give them order. Before we can find patterns, we have to acknowledge the chaos. In unsupervised learning, we do not have labels or categories predefined for us. Like a pile of mixed-up iron filings on a flat surface, we see the dots, but we do not yet see the structure. Our goal is to find which dots belong together based purely on how close they are to one another. This is where we introduce our primary tools, the magnets. We start by dropping a specific number of magnets, which we call K, onto our surface at random locations. These magnets represent our initial centroids. Imagine dropping 3 magnets onto the table without looking. They might land right in the middle of a group of filings, or they might land in an empty space. This initial placement is the starting point for a process that will eventually reach equilibrium. As soon as the magnets touch the surface, the iron filings feel a pull. In the assignment step, every single data point is claimed by the magnet closest to it. If a filing is closer to the blue magnet than the purple one, it snaps to the blue group and takes on its color. This creates distinct regions, where every point in a region belongs to the same magnetic master. We are essentially partitioning the space based on proximity. Now, the magnets must move. We look at all the filings assigned to the blue magnet and calculate their average position or their center of mass. We then slide the magnet to this new central location. Think of it as the magnet adjusting itself to be in the heart of its new family. By moving to the center, the magnet better represents the collective position of all its assigned points. This process is a dance that repeats. Because the magnets moved, some filings might now be closer to a different magnet than before. We reassign the filings, changing their colors, and then we move the magnets to their new centers of mass again. It is a constant cycle of snapping to the nearest force, and then the force shifting to the center of its followers. With every step, the magnets find a more stable and representative home. Eventually, a moment comes when the filings no longer change their allegiance, and the magnets no longer need to move. This is called convergence. Our magnetic system has reached equilibrium. Like filings perfectly sorted into piles, our data is now neatly clustered. The algorithm has finished its work, and we have successfully discovered the hidden structure within the original chaos. But how do we know how many magnets to use? If we use too few, like only 2 magnets for 3 distinct groups, we fail to see the detail. If we use too many, like 10 magnets for the same data, we overcomplicate the picture. Think of it like trying to sort your filings into the right number of bins. Too many bins makes the sorting meaningless. We often look for the elbow in a graph, where adding more magnets starts providing significant improvements in organization. K-means is a powerful way to find order without needing a teacher. By simply dropping magnets and letting them find their center of mass, we can organize massive amounts of information. Remember the steps: pick your K, assign the filings, move the magnets, and repeat until stable. If you enjoyed this magnetic journey into machine learning, subscribe for more deep dives into the algorithms that shape our world. What cluster will you discover next? Subscribe for more visual guides on how machine learning algorithms organize data.